In this video, we're going to create the CAD and simulate the aerodynamic flow around an Ahmed body using Ansys Fluent. So, first of all, just grabbing the Fluent module and dropping it into the workspace. Right clicking on geometry and opening a new design model of geometry. So once Fluent's opened, just select the XY plane and the normal Z axis. And we're going to start by sketching our computational domain. So just create a new sketch. And select rectangle. Just create something that sits slightly upstream and drags downstream a little bit. What we'll do now is just add some dimensions. So we need to create a general length, a general width, and then position it relative to the X and Y axes. I'm just selecting that vertical one there just to ensure that our domain is centralized. So first of all, just selecting our width, V2, so that's currently 11 meters. I'll move that down to 10. V4 is our half width, so I'll create that as 5. H1 is our total length, so I'll just put that to 20. And H3 is our distance upstream, so I'll create that as 5 meters. Once we've done that, we can extrude, and I'll give that a value of 5 meters as well. So just hit generate once you're happy. Once we've done that, we can start sketching the Ahmed body. We need to make sure it's offset from the floor, so selecting the X, Y plane, and then up here, selecting a new plane. We need to make sure it's transformed off the ground plane, because obviously our vehicle is going to be offset. Selecting a global offset in the Z direction, just making sure it's 0.172 meters above the ground as we need from the paper. So 0.172, and just hit generate. We can then create a sketch on this and just get the general dimensions of the Ahmed body. So creating another sketch, but making sure it's on plane 4. We can start with a basic rectangle, and we just want to ensure that its front face is based around this y-axis here. So again, don't be too accurate at the moment. We're just going to put a general sketch in and then add some dimensions again. So general length, general width, and then our half width. So this is just where we need to refer to the paper. So the length H1, I believe, is going to be 1.044, sorry. Width is going to be 0.389 meters. .389, and then we just need to divide that width by 2, which gives us 0.1945 meters. Then we can perform another extrude operation based off that sketch. In this case, we're going to be cutting material rather than adding it. And again, just referring to the paper for the height, looking for 0.288 meters. So once we hit generate, our Ahmed body shape is going to cut out from the domain. So there should now be a void in there. Okay, so now we have an Ahmed body type shape, but we just need to make sure we're rounding the front face off. So in this instance, we've got a radius of curvature on these front edges of 0.1 meters. So I'm just going to add that. So it's currently a bug with Design Modeler that when you do a cut plane through the domain, it shuts down the program. Not quite sure why that is. So I'm just going to perform my actions effectively blind and work with that. So I'm going to use the blend option, and I'm also going to make sure I can select my edges. So just using a box select up here to grab all those front edges here and hide this face here. And hide face, and then you can see my geometry a lot clearer. So glad that front edge worked. Okay, so once I've got my shape, I just select chamfer, select that edge, apply, and say left angle. In this case, I'm going to use a 30-degree slant rather than 5 degrees, and we should get something that looks like that. The paper does have feet included, but what I'm going to do is just leave them out for the moment. You can always add those in later. I'm just going to hide these faces as well because I want to look at the geometry in a bit more detail. So what we do is select the front faces, the rear faces, and the remainder of the geometry as independent bodies so we can determine the individual drag on them. So just selecting this face, this square one, and then these other two. And I'm going to name those. As front. And we know what 5 faces they are. Select these are the side ones. And call those sides. And then finally, we've got slightly hidden behind this. Got this rear slant and rear face. So I'm going to group those together, and we'll call those base. So if you've not heard the term base drag, it just refers to the drag on a bluff body where the flow separates. So once I've done that, I can just show all faces and then go and name the individual boundary conditions. So this front one here, of course that's going to be our inlet. And once you're happy, just generate. I'm going to group the roof and side walls. So I'll call that the side walls, just try and differentiate it. Then we've just got to name the ground, which will initially set as no slip that doesn't move. Obviously we have the opportunity later on then to make it as a moving wall. And finally, the outlet condition. Okay, so that's all my boundaries sufficiently named. So once you're happy, just save and move into the meshing stage of the process. Okay, so the geometry has imported. So again, as we always do, just generate a standard mesh before we begin any refinement. Okay, so now we've got our mesh. What we want to do is just make sure that we've got a sufficiently refined mesh on the surface of the body. So just making sure I've got the faces selected, and I'm going to box select because my geometry is somewhere in there. Just going to draw a big box around, and there it is. It's selected itself. So because it's about 1 meter long, I'm going to make these cells in the order of 5 centimeters to begin with. These are going to be shrunk later on, just performing some initial simulations just to see how everything behaves. And then once we've done that, we can also create inflation layers. So just pick up on the going to create some inflation layers because we want to make sure we're properly capturing the flow at the wall on the vehicle. And we can make these relatively small, so they're going to have a total thickness in the order of 1 centimeter when we've got 5 layers, so hopefully that'll capture the flow right next to the wall. And just let those generate. Just going to hit save, and then we can have a look at the mesh via a section plane. So just selecting section plane and running it through the middle approximately. If we rotate, hopefully we'll see a refined region there. See, we are performing some level of refinement, but it could be a lot more. So you can see our prism layer cells and our slightly finer mesh close to the vehicle. So just shutting meshing down when you're ready, and update it. And once you've done that, just double click on setup to open Fluent. So I'm going to select double precision and 4 processes before hitting start. This is just to ensure my simulation runs quicker because I've got more than one processor on this computer. Okay, so now Fluent's opened up, we can just have a little look. So we've got pressure-based simulation set, and we're looking at a steady state simulation. So in terms of models, we're not going to have any energy, but we are going to have turbulence, so we can leave our viscous model there. Material by default should come through as air. So what we're really interested in here is our boundary conditions. So if we select our inlet, we need to determine an inlet velocity for this. So we're going to be looking at a speed of 60 meters per second based on the Ahmed body paper, and it's got low turbulence density, so I'll put that as 0.5%. Our outlet condition, this is going to be a pressure outlet with 0 relative pressure, and again I'll have to put that as a matching value. We've got more than one wall, so we've got our base, which is the back end of the Ahmed body, got the front of the Ahmed body, got the ground of the domain, the sides and the side walls. So I don't want any slip from any of our Ahmed body parts, but from the side walls I will. So I want that to be a specified shear of 0. So that's just meaning there's no change in velocity because of those walls being present. So we can close that, and because there's no interesting things happening with a mesh, we can just move on to methods. So we can leave our standard settings here. In this case, we can assume pseudo-transient, which is a very stable form of simulation within Fluent. And I'm actually going to do a lot of my data post-processing in CFD post rather than setting it up here. For initialization, we'll leave hybrid, and we'll actually just increase the number of iterations to ensure we get a nice stable solution. And there you go, some external aero-based settings we can use as well. So once you're happy, you just set your number of iterations as a basic value. I'll go for 200 and just hit calculate. Okay, so our simulation has completed. So we can just shut down Fluent and move on into CFD post. So we have our completed solution here. I'm going to first of all just create a section plane in the domain about the ZX plane and colour it. Let's begin just with velocity in the X direction. And as you can see, we've got a massive buildup of boundary layer. This is just a result of having a no slip wall and really coarse mesh cells. But there's definitely flow around the Ahmed body. There's slow velocity in the wake, and that looks approximately what we'd be expecting. So the reason I've come straight into this rather than refining the simulation first is we want to build our expressions to do our post-processing. So first of all, I'm going to start with building one called drag front. So what we're going to do is take the force in the X direction at, so we need our location, which will be that front face. And then we're going to put it over half times 1.226 kilogram per meters cubed. And then we need to multiply that by the velocity. So that'll be 60 meters per second. I'm going to do that twice rather than squaring. And then we need to multiply that by width and height. That's going to be 0.389 times 0.288, which is 0.112 meters squared. So just checking that's correct. Force over half rho u squared a. So that should then give us a CD value there. And then we can duplicate this and call it drag base. So within drag base, we just want to change this to being base, assuming I've spelled that the way the software has. Awesome. And then there'll also be drag sides, which should be negligible here. And we'll just go into location tool just to make sure I selected that correctly or named it correctly. And as you can see, it's much smaller than the other two. I'm going to create another expression called drag total. Just going to put a placeholder in there a second. So in drag total, I'm going to take drag front plus drag sides plus drag base, and going to sum those together. And that gives us a total drag coefficient there. So we can determine the value of each one relative to the total. So taking that a little bit further, I'm going to say percentage base. So we could have drag base over drag total multiplied by 100. And that tells us that the drag contribution of the base is 73.3% in this current simulation. And that means that the sides and front are going to take the remainder. I think it's a fair bet to say that the front is going to be going to contribute the most for the remainder. So just doing this, we'll say percent front. So just put drag front here. And you can see that's 18. So then we've got about 7% just due to friction. I hope you found this video useful. If you did, please like the video and of course subscribe to the channel. It helps more people find us and allow us to help them.